Dear students, today we will study about electric flux density. Okay, electric flux density. This is a vector given as D. Electric flux density is a vector D. Okay. Now you have studied E, right? E in general for a point charge. We have studied E equal to what is it? Q by 4 pi epsilon 0, right? Then if it's a vector R, right, square AR, right, AR. This is the electric field intensity, right? And you know this is depending on epsilon 0. Depends on epsilon 0, right? Now that means that the electric field intensity is dependent on the medium. Each medium has its own permittivity epsilon 0. So the electric field intensity depends on the permittivity of the medium. Okay. So now we have the electric flux density defined as D equal to epsilon 0 E. So you can see that this is independent of the medium. Independent of medium in which you have the electric flux. Okay. That is, it is independent of epsilon 0 of the medium, right? Now you can even think of what you can say. You can think of a electric flux, which is the integral of the electric flux density. Electric flux is given by psi equal to integral over a surface of B dot ds. This is the electric flux. Okay. This is electric flux and it's having the units coulombs. Okay. So that is an electric flux of 1 coulomb. Okay, you can say that one or you can say that 1 coulomb of electric flux, or it's 1 line of electric flux. Flux is from plus 1 coulomb. Okay, you can say that 1 line of electric flux starts from a plus 1 coulomb charge and ends at a minus 1 coulomb charge. That is how you define the electric flux. So whenever there is a plus 1 coulomb charge, a flux of 1 coulomb will start from it and ends at another minus 1 coulomb charge. That is how you define the electric flux psi. Okay. So you can see if you apply the equation, D equal to epsilon 0 E, right? Right. Then you can say that for a point charge, you can have D equal to Q by 4 pi epsilon 0, right? No, sorry, epsilon 0 is not there. Q by 4 pi r square AR, right? Similarly, if you take an infinite sheet of charge, infinite sheet of charge, you can have D equal to rho s by 2 an, right? You can have the infinite sheet of charge like this, right? You have the infinite sheet, it is extending to infinity, right? And an is a unit vector in the direction perpendicular to that infinite sheet of charge. From this infinite sheet of charge has a surface charge density of rho s coulombs per meter, right? So you can say that the direction of D is the same as the direction of the unit vector an. Both are having the same direction. Okay. Now, based on this concept for the electric flux density for a point charge and for an infinite sheet of charge and for a line charge and all, for example, then you can have similarly for a line charge. Okay, if you go and see for a line charge, you can see for line charge, we can have D equal to rho L by 2 pi rho A rho, isn't it? We have derived the equations for the electric field for line charge, infinite sheet of charge and point charge earlier. And from that, if you multiply those equations with epsilon 0, you will get the equations for all these things, right? So that's why I am writing it like this. Suppose if you have a line charge like this, right, and there is a point here, you draw this line. This is rho, right, and arrow is in the same direction, right? The line charge density is rho L coulombs per meter, right? Then you can find out the electric flux density at that particular point. That's how you do. Now we will do a problem. An example we will do. Right. Example. You have there is a point charge of -5 millicoulomb at the point of 0, 0. And the line charge 3 pi millicoulombs per meter. The millicoulomb 3 pi millicoulombs per meter along the y-axis. Okay. Determine D at 0.403. In the solution like this, first we will draw the diagram of this thing. See, this is the y-axis, this is the x-axis, right? And this is the z-axis. You have a point charge at the point 40. X is 4, 1, 2, 3, 4. And y equal to 0, z equal to 0. So you have a point charge of minus 5 pi millicoulomb here, right? And you have a line charge of 3 pi millicoulombs per meter along the whole line, right? You have the 3 pi. It's extending along the y-axis. So this is 3 pi millicoulomb per meter, right? Now you are asked to find out the electric flux density at the point 403, right? So you have a point at 403. This is for x is 4, y equal to 0 and z equal to 3, right? So at this point, okay, this point is 403. You have to find out the electric flux density at this point, 403, right? So you have a point charge at minus 5 millicoulomb at 400, a line charge along the y-axis, and you have to find out the electric flux density at the point 403. Okay. So now we will do this problem. So what we do is the total electric flux density at the point 403 is because of the point charge, right? You can write the total electric flux density D equal to electric flux density due to the point charge dq plus electric flux density due to the line charge dl, right? And the equation for dq, as you know, is q by 4 pi, right, r square ar, right? Just that. Now you know q equal to minus 5 pi millicoulomb, right? What is r? R is 403 minus, right? What is R? R is starting from minus 5 millicoulomb and ending at the point, right? So you can write R equal to 403 minus 400, right? So you can write R equal to 003, right? And magnitude of R will be equal to square root of 0 square plus 0 square plus 3 square equal to 3, right? And AR will be equal to 003 divided by 3 equal to 001. This is actually the unit vector Az, right? So now you can write dq as, q by dq will be equal to, so you can write dq equal to minus 5 pi, right, into 10 raised to minus 3 divided by 4 pi, right, 4 pi into 3 square, right? 3 square is 9 into 003, 1, right? So it will come around minus 0.139 AZ millicoulombs per meter square. That's the value of dq, right? Now we'll go for dl, right? dl, right? dl equal to, we have studied, rho L by 2 pi rho aero. Understand? Now you go to the previous slide and see how aero is coming, right? See, aero, it is from the z axis, right? Aero is starting from the, this is rho, right? This vector is rho, and aero, right, start from here to here. So that is on the y-axis you have x equal to 0 and z equal to 0, right? Any point on the y-axis, x equal to 0 and z equal to 0. So as we have said in the previous lecture, what you have to make is, you also make y the same value as the y of that point. For example, for that particular point 403, y equal to 0. So you choose a point on the y-axis which is also having the same value of y. So if you do like that, you can say that rho, you can write rho equal to 403 minus, rho is a vector, right? 0, 0, 0. I have chosen the same value of y for that particular point on the y-axis from which you are drawing rho. You cannot do anything about x and z. X and z will be 0 on the y-axis, right? So this will give you something like this, that is 403, right? Understand? And what is aero? You can write aero equal to 403 divided by magnitude of rho. Okay, what is magnitude of rho? Magnitude of rho will be equal to square root of 4 square plus 0 square plus 3 square, 16 plus 9, 25, 25, right? So you can write this as 403 divided by 403 divided by 5, right? Now you can do the problem like this. Okay. Now you can write dl. You can write dl equal to rho L. Rho L is 3 pi, right? Rho L is 3 pi coulombs per meter square, 2 pi magnitude of rho square, right? Magnitude of rho, right? Magnitude of rho is 5. Then aero. Aero is, what is aero? 403, right? 403 divided by 5. So you can get it as 0.24 AX plus 0.18 AZ millicoulombs per meter square. So the total D will be equal to dq plus dl. You can write it as 240 AX plus 41.1 AZ micro coulombs per meter square as given in the text. So that's the answer for this particular problem. Okay. Now we will study about something called the Gauss law. Okay, study about the Gauss law and the Maxwell's equations. Gauss law states that the statement is like this: total electric flux, psi through any closed surface is equal to the total charge enclosed by that surface. This is the statement of the Gauss law. The total electric flux through any closed surface is equal to the total charge enclosed by the surface. You can mathematically write it like this: psi, you can write it like this: psi equal to the charge enclosed, Q enclosed. Okay, understand? So you know psi equal to integral S d dot ds, isn't it? Psi equal to integral d dot ds. So, and also you know Q equal to integral over a volume rho v dv, isn't it? So suppose if you have a closed surface like this, suppose you have a small elemental area vector ds, and suppose if d is the vector going like this. Okay, so you integrate that d over the whole surface to get the total flux density over the whole surface flux. Okay, suppose if this surface area encloses a volume, okay, a volume with a small volume element dv, right, and the charge density in this volume is given by rho v coulombs per meter cube. Okay, so this is a very small volume element, okay, not an area. This is an area element. You have a volume v that is enclosed by a surface S, right? This is a surface S, and this volume is the volume V, right? You have a volume V enclosed by a surface S. So you take the integral of the flux density over the whole surface. That will be equal to the integral of the charge density for the whole volume, right? Now you can equate these two things. So you can get integral d dot ds equal to integral over the volume rho v dv. You have to remember one thing: d and ds are vectors. It's a dot product. Integral when rho v and dv are not vectors, they are taken as scalars. Okay. So now from this you can say that if you apply the divergence theorem, right? If you apply the divergence theorem, you know that del dot S, you studied divergence theorem previously, right? D dot ds equal to integral over v del dot d dv, right? That's the divergence theorem. From this you can get an equation like this. rho V equal to del dot D. That's a very important equation. It's called the first Maxwell's equation. You can say this is Maxwell's equation 1. Okay, this is Maxwell's equation 1. Rho V equal to del dot D. Okay, there are 4 Maxwell's equations. So this is the first Maxwell's equation. So what it says is the volume charge density is the same as the divergence of the flux density. Okay, the volume charge density equal to divergence of the flux density. That's what Maxwell's equation says, right? Volume charge density equal to volume charge density equal to flux density, divergence of flux density. This is a very important equation in electromagnetics, this Maxwell's equation 1. Okay. Now we will see what is the Gauss law. Suppose see you have a volume like this. Okay. Here you have some 6 coulomb, right? And here you have minus 3 coulomb. Both are inside the volume. Okay. Inside the volume you have a minus 3 coulomb as well as a 6 coulomb. Okay. What is the flux leaving this volume? Let us call this volume as V1. So you can see flux leaving volume V1 equal to 6 minus 3 equal to 3 coulomb. Right. Understand? So the flux leaving a volume will be equal to the charge enclosed by the volume. But suppose if you have another volume like this, okay, but there is a charge of 3 coulombs here. Okay, there is no charge inside that volume. So you can say that, suppose if you call this V2, you can say that flux leaving V2 will be equal to 0 coulomb. Okay, because there is no charge inside the volume, even though there is charge outside the volume. So Maxwell's, this Gauss law gives how much flux is leaving a particular volume, and that particular flux is equal to the charge enclosed by that volume. So this is something that you have to remember. Okay. Now we'll see something about the applications of Gauss law. Applications of Gauss law. So for example, for a point charge, if you take a point charge, okay, you have a point charge here. Okay. So what we can do is I want to find out, this is a point charge Q here. I have a point here P, right? I want to find out the flux density at this point. What I do is I will simply draw a sphere around that point charge Q. Okay. Understand? This is what you do. Okay. So this is the point P. I have a point P here, point P. And I want to find out the flux density at this particular point. Okay. So you can say that what you do is simply I will draw a radius like this. Okay. R. Understand? You can say it is a vector, radius vector. And flux density at point P, D, point P due to Q equal to Q by 4 pi R square AR. AR is a unit vector in the direction of R. This is a unit vector, right? Unit vector. That's how you find out the flux density at a point P due to a charge Q, a point charge Q, right? Now, similarly, if you take an infinite line charge, okay. Second case is flux density D due infinite line charge. The second case that we are studying, infinite line charge. Right. I have a, for example, I will draw a diagram like this. This is the y-axis. This is the x-axis. Right. And this is the z-axis. Right. And I have an infinite line charge along the y-axis, for example. If I have an infinite line charge along the y-axis, it's extending on both directions. Okay. A line charge on the z-axis, right? Suppose if I want to find out the flux density at the point P, right? What I do is I will draw a perpendicular from the line charge and let that perpendicular be given by rho, the vector rho, right? Understand? Now, I'm not going into the derivation of that particular thing. Okay, I will just give you the equation. Okay, you can say that D equal to rho L by 2 pi rho, magnitude of rho, then you can write it as a rho. Rho is a unit vector in the same direction. Unit vector. Clear? That's how you find out the flux density at point. You can say this is flux density at point P. Okay. That is what you have derived now here. I'm not going to the derivation of this because in the case of electric field we have made the derivation earlier. That's why. Okay. Now the third case is C. That's the third case. Flux density due to infinite sheet of charge. And you have a sheet of charge like this. That is something that we have derived earlier. You have an infinite sheet of charge like this, right? It's extending in all directions. Okay. And you have a normal vector like this, isn't it? That is given by an. It can be ax, ay, az, or whatever it is. Suppose if it is in the z direction, okay. Suppose if it is in the z direction, you can say this sheet is in the xy plane, right? X, and this is the y, and you can say that if the sheet is in xy plane, right? Isn't it? If sheet is in xy plane, then you have an equal to az. If it is in the yz plane, you will have an equal to ax. If it is in the xz plane, you have an equal to x. If it is in the xz plane, an equal to ay, right? So you can write the flux density as D equal to rho s by 2 az. Okay, in general it is rho s by 2 an. Okay. Now we will have another case, uniform charge sphere. That's the last case that we will study. case D. Charged sphere. So if I have a sphere, okay, I'm having a sphere here. Understand? I have a sphere. I have a sphere here. Okay. Then what I need is somewhere one must know I will do it with better way. That's better. I have a sphere here. Okay. I have a sphere. Okay, there's an inner sphere. That's a there's an inner sphere here. And this sphere is having a radius of, you can say the radius of sphere equal to A, right? So this is a sphere with a radius A. This sphere is having a radius A, and the sphere is having a, this particular sphere is having a volume charge density of rho v coulombs per meter cube, right? Now I want to find out the electric flux density at a point D, okay, and you can draw a radius from that center of the uniformly charged sphere as R, okay. If the point is outside the sphere, you can say that R greater than A for point outside the sphere, right? Outside the ഹലോ അസ്സലാമു അലൈക്കും പറയൂ ഞാൻ റൂമിലുണ്ട് ആ ആ അല്ല എനിക്കെന്താ ഉച്ചയ്ക്ക് ഇവിടെ പോകണമെന്നേ, പിന്നെ എൻ്റെ പവർ ഓഫ് അറ്റോർണി ഉണ്ടാക്കണം, VFS, അതിൻ്റെ അവിടെ പോകാനുണ്ട്. അപ്പോൾ അവിടെ ഇങ്ങനെ പോകാൻ വേണ്ടി നിൽക്കുകയാണ്. 2:30 പോയാൽ മതി. 2:30 അപ്പോയിൻമെൻറ്റ് കിട്ടിയത്. ആ ഇല്ല, ഞാനെന്താ പറയുക, ഞാൻ കുളിച്ചിട്ടൊന്നുമില്ല. കുളിച്ചിട്ടൊക്കെ ഇറങ്ങണ്ടേ? ഓക്കെ. നിങ്ങൾ ആദ്യം നാളെയാണെങ്കിൽ പറ്റുമായിരുന്നു എനിക്ക്. ഇൻഷാ അല്ലാ. അസ്സലാമു അലൈക്കും. ഓക്കെ, ജസാക്കല്ലാ. എന്നായിക്കോട്ടെ. അസ്സലാമു അലൈക്കും. A cubed by, for example, sorry, for r greater than a, for example, r greater than a in this case, if the point is outside the sphere is that green sphere. Okay, for the point is outside the sphere, we can say that the d is a cubed by 3r square and rho v, okay, rho v ar, right? And suppose if the point is inside the sphere, okay. Suppose if you take any point inside the sphere, okay, inside the sphere any point if you take, for that particular point you can say that 0 less than r less than or equal to a, and for that case you can write d equal to, okay, r by 3 rho v ar, okay. That is how the thing is for a charged sphere. So you see, if the point is outside the sphere, it is r greater than a, d is given by the first equation, equation 1, okay. And if the point is inside the sphere, d is given by equation 2. Understand? So that's how you find out the volume integral for this particular case. Understand? Now what we can do is we can do a simple problem. Okay, a simple problem example I will give you. That would be enough for you. An example here. You have an example here. Example, you have d equal to, you are given the flux density is given by z rho cos square phi az coulombs per meter square. That's out. You are given d. Okay. You are asked to find out, calculate charge density at 1 pi by 4 3. Remember, this is in pi by 4 3. This is a cylindrical coordinate system, right? Understand? So what is the charge density? You know the charge density is given by the Maxwell's equation, rho v equal to del dot d. You find out the divergence of this thing. So you can find out the divergence as rho cos square phi. That will be the value of the divergence. Okay. So that we have to find out. It's very simple to do because you know already how to make the divergence, right? Now another question is calculate. B part of this question is calculate total charge enclosed enclosed by the cylinder of radius 1 meter with minus 2 less than or equal to z less than or equal to 2 meter, right? So you see, this is very simple to do. You know q equal to integral over v rho v dv. Okay, so that will be rho v is given by this particular thing, right? Integral over rho cos square phi, that is rho v, isn't it? Rho cos square phi, then dv, elemental volume in the cylindrical coordinate system is given by rho, dv is given by rho d phi d rho dz, right? And you can write the integral is a triple integral, right? Triple integral. So you have z equal to minus 2 to 2, because it is given as minus 2 less than or equal to z less than or equal to 2 meter, right? And phi equal to, you can give phi equal to 0 to 2 pi, right? Because the cylinder, the whole phi will be 2 pi radians, right? And what about rho? Rho is from 0 to 1 meter, right? 1 meter, 0 to 1. So you can find out this integral, rho cos square phi rho d phi, sorry, rho d phi rho d phi d rho dz, right? Rho d phi d rho dz. If you find out the integral, you can get the answer as 4 pi by 3 coulombs. That's the answer. So that's all for this particular class. And I will stop here. So I will see you in the next class.